180. Alright, so with hypothesis testing, no one will have heard of hypothesis testing before, eh? No, cool. So when we do any statistical investigation, we have to set up what we call a hypothesis test. Okay, that is where we write a set of statements to say what we're going to investigate, kind of how we're going to investigate it, and what mathematical values are going to be important when we investigate it. So there's some little blurby thing on page 180 which is about Macho Man Dan or something, who I'm pretty sure is saying that he's so masculine, if he has a kid, it's more likely to be male than female because he's masculine. Some nonsense along those lines. And we're just going to talk about how we could do a statistical investigation to find out about this. So, obviously, the probability of male-female was probability of 50%. We've got 50% probability of male, 50% probability of female. If we look at international statistics on male-female gender splits, I think there's actually a tiny bit more female than male in the world. And that's probably to do with the fact that you guys live longer. Because men are stupid. And we do stupid things and our bodies decay very quickly. So there's very good statistical evidence to suggest that it is almost a 50-50 chance of male-female at birth. Okay. So this would be a form of binomial distribution that you'd investigate, because you're either male or you're not male. Okay, that's a binomial. I'm looking at the room and I'm thinking, how many of you actually remember binomial expansion and distribution from last year? A few of you, okay. If you forget, you can always look back in that textbook, because I think it's chapter 6 or 5 maybe. Yeah, 6. Chapter 6 is all about binomial distribution. You should have done it. Okay? So, basically, you can break down the probability of certain circumstances using binomial distribution. So, if you were to, for instance, to say, what's the probability that none of his kids are male and all the other kids are female, you can use binomial distribution to calculate that the probability is 1 out of 256. Okay, if you don't remember the binomial distribution, that is your NCR. Yeah.
Californian Republic.
P to power what?
The Californian Republic.
P to power R times Q to power N minus R, that thing. I don't know what he's on about. Okay, that's your binomial distribution for when you B and P, which is British National Party for the New Californian Republic. So just be aware of that. So they've calculated these probabilities. You also need to remember how to calculate these probabilities, because you are going to need to do the maths yourself. But the probability of having 0 boys, 8 girls, 1 out of 256. Okay, very low. If we look at 1 boy, that's 8 out of 256, 2, 28. And obviously it goes all the way down through that table of all the probabilities of those events happening. Okay, and they've put it into a little diagram at the bottom. Okay, what does that diagram remind you of? Anything? Kind of like normal distribution. Okay, and we can use normal distribution as an approximation of binomial distribution in certain circumstances. And did you do a bit of approximation last year with normal for approximate as binomial? Yeah. But when like n is really large and stuff, you can do it. So, your continuity correction error, that's all that jazz. Okay? So we need to have a bit of a memory. Okay? So that's the distribution table. Okay? So he was saying that because he's so macho, the probability of him having a boy will be greater than average. Okay, the average being 0.5, yeah. The average probability being 0.5. So we're trying to find out whether he is exceptional, as in he is outside that norm. So the set of hypotheses we're going to set up are our null hypothesis. Okay, the null hypothesis is always there is nothing special happening. Okay, so our null hypothesis in this case is the probability that Dan will have a boy is 0.5. Yeah? Does that make sense? Yeah. By the way, we're on page 182 at this point. So if you're wondering what I'm referring to defining terms there. Okay. So the probability he will have a boy is 0.5. Because he's saying that he's more, macho, and that means more boys, that would be saying that the probability of a boy would be greater than 0.5. Okay, that's what we're going to test. Or at least that's what we're going to talk about the test of. So that would be called our alternative hypothesis. These are given two different symbols. So our null hypothesis is written as H0. So that's your null hypothesis. And H1 is your alternate hypothesis. Alternative, sorry. I was just making sure that I was actually displaying. Okay, so those that's how you tend to write it. Okay, and you write it as a sentence. You can't just write H0, P equals 0.5. It's not wordy enough. In stats, they're going to want you to write sentences. So for Dan's case, you'd say H0, P equals 0.5, comma, the probability Dan will have a boy is equal to 0.5. Yeah, H1 would be P is greater than 0.5, the probability, and you tend to repeat yourself quite often with these hypotheses. Dan will have a boy is greater than 0.5. Okay? And you've got to get used to writing that. I would love to just be able to write P greater than 0.5, P equal 0.5, but they don't give you the marks in the test if you just do that. Okay? And that's our alternative hypothesis. They mention in here that if you want to talk about more than one hypothesis at a time, you're talking about hypotheses. And we'll talk about the kinds of tests for our, because you need to understand the difference between what we call a one-tailed test and a two-tailed test, but we'll get into that. We talk through some unreasonable probabilities here. Okay, so let's move on. So, this is how Dan could have worded his hypothesis test. Oh, significance level. Didn't mention that. Was it mentioned up here? Don't think it was. Oh, yeah. Okay. So, when we look at our probabilities, we have to decide what significance level we are testing to. Okay? The significance level is saying if the probability is beyond a certain point, we can say to a certain significance level that the situation is either true or false. Okay? So if there's only a 1% chance of it happening, and he's within that 1%, then we can say that the claim he is making is true. If it's not within that 1%, then the claim he is making is not true. So if we look back at that distribution, if he's up here at 8, if he's got 8 boys out of 8 children, that's super unlikely. Okay? So we can potentially say to a certain level of significance that he is accurate with his claim. Okay? If he's having 7 boys, we don't just consider 7 boys, but we also consider the potential of more than 7. So you'd look at all of that probability, the 7 and the 8, and test that to a 1% significance level, and that might also be less than 1% of whatever significance level you're testing to. So then that also might be significant enough to say something is happening here. Okay? So that's what the significance level is. In this example, they've stated we're going to be testing to a 1% significance level. You don't need to generate the significance level yourself. Generally, in the questions, they will tell you what significance level to test to. It's normally 1%, sometimes 5%. It's interesting. If you look on your formula sheet, on the normal distribution side, what you'll notice at the bottom is critical values of a normal distribution. Because we'll also be doing hypothesis testing with this normal distribution as well, not just binomial. And at the bottom, there's different percentage points. Okay, and they're kind of what we're going to be referring to when we're doing this with normal. Okay, so there's like a 95%, which is 0.95. There's a 97.5%. There's a 99% value that you would test to, and we'll talk about that a bit more when we get towards that. So on page 183, at the top of 183, they've set the situation up. So they're saying testing at a 1% significance level, Dan's claim that his children are more likely to be boys than girls. The answer would look like this. We have a null hypothesis, H0, P equals 0.5. They've written as boys and girls are equally likely. Alternative hypothesis, H1, P greater than 0.5, boys are more likely. Okay. Significance level, they've stated underneath as well to say, hey, what are we actually testing this hypothesis to? And they've suggested 1%. Okay. So if he had 8 boys, the percentage possibility of that happening would be 0.39%. So with regards to the binomial distribution, which I'll draw on here, I'm just going to draw it as a curve rather than bars, which is wrong, okay? But there's bars all the way along here. The 8 children point, 8 or more children, the probability was 0.39%, okay? Because we're testing to a 1% significance level, it's less than 1% chance of that happening, which means that it's significant enough to say he is Macho Dan. Does that make sense? If he was having the 6 children, and I don't actually know the value for 6 off the top of my head, and let's say the probability of that was 3.5%, okay, the probability that he has 6 or more children is 3.5%, then that's not significant enough to say that he is special. Does that make sense? Cool. So that's what we're referring to when we talk about hypothesis testing. What's the probability of this situation happening, and does that meet our significance test? Okay. But you guys need to learn how to write your hypothesis statements for H0, H1. And I think that's kind of what the focus of today's lesson is in chapter 8a. But there's other things to consider. And these aren't something that you're going to need to focus too much on with regards to answering a question in a Cambridge test, because it's mainly more on the mathematics side. You've got to do your setup, H0, H1, you've got to write those things down, 1 mark generally. You've got to do your actual mathematics, which might be 2 or 3 marks for the actual mathematics side of things, and then you get an extra mark at the end for writing an answer. You know, did the thing happen? But just some other stuff to consider. This is for your general knowledge of statistics. You need to consider, did he come up with the question before he got the solution? Okay, that's a thing for statistics, is if you're going to investigate something, you need to write a hypothesis test before you investigate it. You can't investigate a scenario and retroactively write a hypothesis test, because that's data manipulation, basically. Okay, it's finding a solution and then saying this is how I'm trying to think of a good analogy, but I can't off the top of my tired mind, because this has been more work than I've done in the past 4 months today. But basically, he could have found out that actually has more girls, and then he comes along and says, I'm actually femininely virile or something, I don't know. Creating his claim after finding the solution. Does that make sense? You can't do that. It's not allowed. It's not acceptable. It's a bad test if you do that. Okay. Was the sample involved chosen at random? Okay. Did he have 8 children with the same woman? Maybe she's macho. Maybe it's got nothing to do with him. Maybe she's macho lassie, I don't know. Macho lassie Mary. Is anyone in here called Mary? Yes. No. Good. All right. Okay. And it's actually all down to that. Or was this 8 random women all across New Zealand? What a player. And he's actually knocked up a load of different people. And, that's a random sample. For statistics, you need a random sample. You can't have... Have you talked about sampling before? No, we'll talk about sampling in one of the exercises this year, but you can't have a non-random sample for your data. Okay, it becomes statistically biased towards a certain outcome when you have non-random sampling. Does it actually test the claim? Okay, does the statement, him saying that he's got macho chromosomes, can that actually be tested by finding out whether he has more boys with greater probability? Okay, he's claiming he's so macho that he's going to have more boys. Are they correlated? Does being macho actually mean you're going to have more boys? No. These are things you have to potentially consider when doing a real statistical investigation. But for our purposes, you probably don't need to worry too much about these statements. Okay? There's a step-by-step ideal way of setting up a hypothesis test, so you need to always establish your null and alternative hypothesis to begin with, decide on your significance level, get suitable random data that are all independent, conduct a test, and interpret the results based upon the original claim. Okay, so you need your original claim before you can do a test. Obviously, testing at 1% significance level, I've mentioned that. There are other significance levels to test at. If we were to test at 0.1%, his claim would not be true. If we were to test at 5%, more claims would potentially be true. Right, there's another one for you. Example of dice. So let's quickly rush through this one, because I don't want to talk all day. Stats, too much talking with stats. I much prefer pure with regards to talking wise. So Leonora claims that a die is biased with a tendency to show the number 1. Okay, so she's saying that that dice is showing the 1 more often than it should be. The probability of rolling a 1 is a 1/6. Yes. Yeah. Good. So we're going to test her hypothesis to see whether the probability of rolling a 1 is greater than a 1/6 or equal to a 1/6 to a certain degree. So they've written the null hypothesis H0, P equals a 1/6 for dies unbiased. Alternative, H1, P is greater than a 1/6, implying that it happens more frequently than not, than it should do. The die is biased towards 1, and we're going to test out a 5% significance level. So she rolled the dice 20 times and recorded down below how many times each one appeared. Cool. And then she also wrote down the probabilities of it happening based upon a correct number of times. If that makes sense. Sorry, I'm real thirsty. So she calculated what's the probability of rolling 1/6. 1 out of 20 times. The probability of getting 2 1s out of 20 times, 3 1s out of 20 times, 4 1s out of 20 times, all the way down to 20 1s out of 20 times. Yes? No? Yes. Does that make sense? Any questions about that table? No. Okay. So, it says calling X the number of ones occurring when a die is rolled 20 times. The probability of 6 or more ones is given by this. So, 6 or more ones is taking into consideration everything on that table, starting at 6 all the way up to 20. So we're going to add all of those probabilities together. Okay, 6 or more, adding them all up. How else could I do that? Rather than adding up every probability from 6 to 20, is there another way I could do that?
Subtract it from the first 5.
From the first
5.
First 5? 0 to 5. 6. First 6. Yeah. Okay. So, yeah, instead of adding up 6 to 20, I could do 1 minus the probability of 0 to 5. You remember that?
Yes.
It's a lot of people who look real like we expect to know things.
Really vaguely remember.
You really vaguely remember. Well, basically 1 minus probability of 0 to 5 would be equivalent to the probability of 6 or more. Okay? Please remember those things. And they said that the probability of it being 6 or more was 0.1018, so about 10%. And because 10% significance level is greater than 5%, that means it's not actually that, important. Okay? If I refer back to a distribution, a drawing of a distribution, basically what they've got going on here is this, where 6 is here, 20 is up there, 0 is there. The probability of 6 or more is about 10%, which does not fit within our significance level of 5%. Okay? It would only be if it was within that region that it would be significant enough to say it's biased. Okay? Even though 6 ones out of 20 rolls is not that likely, 10%, it's not significantly unlikely. Yeah? Cool. So that's how they've calculated it. Then we're going to write a little statement saying the null hypothesis, since this null hypothesis is accepted, is Lenora's claim is rejected at the 5% significance level. Okay? So you just say, hey, it's not significant enough, so I'm still sticking with my null hypothesis. The alternative hypothesis is rejected. Leonora is a liar. She claimed wrong. Okay? There's a picture they've drawn of it, actually, because binomial distribution should be bars. It shouldn't be a curve like I keep drawing, because it's not continuous data, but it's just easier for me to draw quickly. Blah, 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 blah. And then questions. So basically, all I want you to do for the next 10-15 minutes is create hypotheses for each of those scenarios written down. Okay? We'll worry about the mathematics side of this tomorrow. This is just purely the writing the hypotheses side. Does that make sense? Thumbs up? Thumbs up.
We just do the same thing, but with our own numbers.
Well, with the situations that they state.
Just like with die and with...
So if you look at the first question, which is on page, flip, other way, you're going wrong way. Next page. So if you look at the first question, it's about Mrs. De Silva. Oh, no, sorry, yeah. So Mrs. De Silva